Hello. So this is the summary for lecture 4. First, I made an announcement that the quiz on Thursday in lab will have 3 problems, 2 similar to the homework, and 1 mom calculation. You'll have 30 minutes, and we'll be providing you a summary sheet of distributions, the same summary sheet that you had in Stat 134. Today, what we're doing is giving an intro to MLE, properties of MLE, in particular equivariance and consistency. Then we're going to review chi-squared and t-distribution, because we're going to need that to talk about confidence intervals for the MLE of mu and sigma squared, giving an exact form for like a 95% CI. Okay, so MLE, maximum likelihood estimator, you're fixing your data, and you are having your parameter theta as your variable. So you can think of the likelihood as a function of theta, and what we're looking for is given our fixed data values, what value of your parameter is most likely, maximizes the likelihood function. So most of the time we're going to be assuming that our random sample is IID. So our likelihood will factor as a product, and then it'll be nice to take the log and look at the log likelihood. Now, log is monotonically increasing, so whatever value of theta maximizes the likelihood function will also maximize the log likelihood function. And so this is an optimization problem. We take the derivative and set it equal to 0, and the solution is the maximum likelihood estimator. Now, generally there's no guarantee that there's a solution. There could be multiple solutions. So generally we have to make assumptions about our likelihood function, and it may be that MLE is not a good estimator to use. We might need, for example, to use a mom estimator if the likelihood function is not nice. So just a simple example to start. Just imagine you have one data point, a flip of a coin, probability P. So this is a Bernoulli P. Our likelihood function then would just be P to the power x 1 minus P to the power 1 minus x, right? So x is either 0 or 1. If x is 1, then your mass function is P, and if x is 0, then your mass function is 1 minus P. So we take the log of both sides, we take the derivative, and we find the ML estimator is x. That totally makes sense, and you can see it in the diagram here. In this diagram here, you can see that if x is 1, so f1 given p, the likelihood of p is just p. That's the graph of that is just a straight line of slope 1, and the maximum of that occurs when p takes the value 1. Again, x is 1, so it is consistent. Okie doke. So another example, x1, xn is IID exponential, and here we get the same estimator that we got for the mom estimator, 1 over x bar. here's the problem we did last time. Last time we looked at this density over here and looked for a MOM estimator. Now we're doing it as a MLE estimator, and you get a different answer here. The details are pretty easy. Let's look at another example of the gamma distribution. This is right out of the book. Example C. This is an example where the MLE estimator can't be written in a closed form. So we need to do this computationally. And so this highlighted equation right here, we're going to find the max of this using the function optim in R. And I've posted this code in B Course's pages in class exercise, so you can use this code for your homework in the future. It basically is an example where, this is actually the example in the book. I just wrote out some data for you that follows a gamma distribution, and you're trying to figure out what the parameters of that gamma distribution are, alpha and lambda. And so we can see the graph here is a graph of gamma looking distribution. So we're going to be using an optimization method, and optimization methods need an initial point, and so we use the MOM estimate, which we can calculate because we already know the MOM estimator, and so I just basically, we can calculate that from our data, which I do here. So that's our initial point. And then this function right here, so this function right here is this one up here. It's actually the negative of it, because the optimization function we're using finds the minimum. So I'm negating a function where we were looking for the maximum, so that we're now going to find the parameters that give the minimum. And so the function optim, you can look in the console, type $optim to learn about the arguments for this function. So one question that came up in class today is, what is the optimization method? And I forgot. So it turns out I checked. So the default optimization method is just it's a very slow but robust method that just uses function values. If you want to use Newton's method, you need. Let me see here. I wrote it down, but I'll write it again. So you need method equals BFGS. So in the argument, if you write this here, that is Newton's method. Not quite as robust to initial values, but very fast. So if you end up not converging to a value quick enough, then you can try Newton's method. Okie doke. And just notice the values that we get are different than the MOM values. So here compared to here. Okay, properties of the MLE. properties of the MLE, we have first